Let me first start with a disclaimer, which Professor Amula pointed out, that a paper by Heisenberg, matrix mechanics, sorry, this is the error, I just did it just now, appeared in 1925. And that was the first paper in Ananda physics. And then another paper appeared here in Europhysics journal, quantum theoretical interpretation of kinematical and mechanical relationships. Both of these were in 1925, but the wave mechanics came first to be studied in 1926. Just for the history to correct, and because Arbola pointed out, so I thought it's my duty to correct the history. So, yeah, so now I go back. First, I wanted to finish what I could not finish yesterday, and that was the point of the couple cluster and the size extensivity. This question is very important also in the context of DFT. That is the reason I wanted to bring up this question first. So let me see where I am. Yeah. So I was looking at various ab initio methods, and one of them was which is today the gold standard, is called the couple cluster. And yesterday I described how the configuration interaction function looks like. Starting from Hartree-Fock, you have doubly excited, singly excited, triply excited determinants, and so on, right? And if you do all of them, then it is full CI in that basis. But it's a linear expansion. So what happens is that you form a Hamiltonian matrix in those determinants and simply diagonalize. So linear diagonalization problem, very simple problem. So CI is a very simple problem. In some sense, it is just expansion of the wave function in a basis. The basis is now basis of determinants. Hartree-Fock is one of them, then all other determinants. And those are formed by those virtual orbitals. We told that there are more virtual orbitals, and those are very, very important. But coupled cluster has a very different philosophy because of the fact that it is a nonlinear wave function, as you can see. Just wanted to tell those who are not really familiar with the second quantization that these operators are used in a second quantized notation, the Tn operator, and you will see that there are some daggers on the top, and which means those are created, and those which have no dagger, they are annihilated. So for example, the first one is A1 dagger, I1 dagger. I1. That means that an electron is destroyed from I1, I, and created onto an A. And then A1, then A2, I2, AN, IN, which means I have now excited N orbitals from occupied I1, I2 to IN and put them in the virtual. So what have you generated now? You have generated n-tuply excited configuration, right? If that number string is only 2, then it is doubly excited. Otherwise, it is n-tuply excited because there are n number of excitations. Excitation essentially means one creation, one annihilation. So annihilation is where there is no dagger. So this is a annihilation. So this is an annihilation. The way I have written, this is a creation. This is a creation. And the I is an annihilation on I. So you can use any symbol, but this is generally what is used for the second quantized symbol. So the T operators are excitation operators. Just like CI determinants are also excited determinants. I can write CI also in second quantization. Usually people don't write CI in second quantization, but one can do the entire thing in second quantization. But here the important part is not that I'm writing in second quantization, because that can be done for CI. If I write instead of exponential t, if I write 1 plus t, it will become exactly CI wave function. So for example, this wave function with this notation, let me write down this notation. So if I write this psi as 1 plus, maybe I should use the white chalk.
Yellow is the best.
Yellow is the best? Okay. If I use psi as 1 plus t, where t is t1 plus t2, on Hartree-Fock, then this is exactly CISD wave function. Yesterday I described that. That means it has a Hartree-Fock determinant And T1 is basically all singles. I have a sum. So T1, if you take n equal to 1, then there is one creation, one annihilation. All singly excited. This is all doubly excited and so on. So that becomes your CI wave function. Okay, I can write it in second quantized notation, it doesn't matter. But the difference with couple cluster here is that this thing is now constructed as an exponential T1 plus T2. There can be other terms, but I'm just showing a similarity with this. And this then will be called couple cluster singles and doubles. Here also you have a singles and doubles, but they are entirely different, as you can see. What is the difference? If I expand this, I will have 1 plus T1 plus T2 as the leading term. But I will also have a square of T1, square of T2, cross term, and all possible products of T1 and T2. So this makes this wave function much more accurate. Because once I have, let's say, T2 square acting on Hartree-Fock, what will it generate? It will generate one doubly excitation, another doubly excitation. So this will effectively become quadruply excited CI. That is a very important part. So I will generate a configuration which in previous term that I wrote will be phi, ij, kl, a, b, c, d. Note that I introduced the symbol in the last class. So that means I have a 4-body excitation from IJKL to ABCD. And these kind of excitations are not there here because I have only a T2. So psi CISD is just doubles, whereas psi CCSD can have quadruples. I'm writing one term. You can have a hextuple, T2 cube. You can have T1 cross multiplied with T2. So several ways one determinant can be formed, and that is very important. But most importantly is that we can go to very higher body excitation, so that makes it very accurate. But more importantly, and this is a very good work by Oktay Sinanoglu, those who are interested should read Sinanoglu's paper in 1964, I think, Advances in Chemical Physics. If I remember right, it's ACP. I hope many of you would, just like Lovedeen, Sinanoglu did a lot of work. He's a Turkish scientist, very brilliant scientist, Dr. Sinanoglu. He wrote a paper, I think, in ACP volume 6, 315, if I remember, 1964. This paper was actually the precursor to couple cluster, after which Jerry Chizek in 1966 did his first paper on couple cluster, also in JCP. That was in JCP, sorry. That's the review article in Advances in Chemical Physics. And what Chizek did was actually to put a second quantized notation on Sinanoglu's work and solve the equation properly, which Sinanoglu somehow did not do. Sinanoglu understood the problem and left it. And there are many such brilliant people who lose interest in the details. But the understanding was all there in Sinanoglu. What Sinanoglu said is the following, that this particular excitation by itself, 4-body excitation, the probability is very less. The chances of, why it is less? Because in a special orbital, there are only 2 electrons. So the 2 electrons can come close together, very, very qualitative argument, and then get excited. 4 electrons are not very easy to come together because they are in 2 different special orbitals. In addition, the Hamiltonian is only 1 and 2 electron operators. So it can combine 2 electrons very easily, effectively. So he said, this is Sinanoglu's pair correlation theory. That is actually given here. So the correlation takes place in pairs, which essentially means CISD is good because you have the T2. You have the double excitation. Nothing wrong with CISD. But CISD is incomplete. Sinanoglu said there can be possibilities like here there is an I and J pair. There is a K and L pair. This is getting excited to AB. That's one doubles. But simultaneously, one KL pair can get excited to CD. So that means 2 pairs, they are getting excited by pairwise. But so to say, they are taking place at the same time. So what you see is a quadruply excited configuration. This was a very interesting qualitative idea that the Sinanoglu gave. And this excitation, what is the probability of this excitation? Probability of this happening and this happening. So it should be the product of this amplitude times this amplitude, because it's a simultaneous excitation.
And if you look at now T2 square is exactly doing that. It's a product of two T2, one on IJAB, another on KLCD, generating this configuration. Of course, there is a half here, but the half simply comes because so that you don't do over counting. Because this is sum over all IJ, this is also sum over all KL, they are dummy indices, so you should not over count. So that is very simple, that half factor, and that also comes into exponential in a very systematic manner. So Sinanoglu explained this pair correlation, that although it takes place in pair, you can have a pair-pair interaction. So this is what we call pair-pair interaction, and so on, plus pair, 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 and so on. But the probabilities will keep on decreasing. Yes.
So this is like taking the fourth order perturbation, some terms out.
Yes, yes.
It becomes like when you do the diagrammatic technique, dropping some diagram.
Yeah, so couple cluster, yeah, since you hit this point, couple cluster is often called selected diagram summed up to infinite order. So I select only a part of those diagrams in the higher order, and then I go up to infinite order, as you can see. In a many-body, strictly in a many-body sense, it's infinite order. And so that is how the couple cluster and perturbation is. Yes, so couple cluster and perturbation has a very similar thing. But it is an infinite order perturbation, but only of selected diagrams. So what are those selected diagrams? The important ones. And that is where couple cluster scores. It doesn't do brute force infinite order perturbation. It takes care of infinite order, only of selected diagrams, and that infinite order summation comes very analytically. So that is the second advantage, otherwise you can't do it, yes.
Maybe a naive question. So when CCSD already has T2 square, T1,
T2Q.
T2 and so
Yes,
on and
yes,
so
yes.
forth, why do we need to go to CCSDT?
Okay, that's a good question. So let me first say, Sinanoglu actually address this. So what he's saying is that CCSD has a T1 into T2, which is a three body by this same nomenclature. If I have I to A, I can have a JK pair going to BC. Okay, so this is effectively IJK going to ABC, which is triple excited, phi, IJK, ABC. So what he is asking is that this is a T1, this is a T2, and a product of T1 and T2 exists here because of the nature of exponential. So I don't need T3, that's what he is telling. The point is that this particular triple excited configuration is a product of an independent single excitations and a pair excitations. But this is not all. There is a small probability of these three particles coming together and getting excited. Although the probability is small, there is a small probability. So if to make it exact, you have to have T3. Similarly, there is a small probability that all these four particles can come together. Probability is only small because of the Pauli exclusion principle, but there is a small probability. So indeed, T3 is very small. T4 is actually not, T4 is also equally small, but T2 square is not small. That is very large. But that is taken care. So of course, if you do CCSDT, it is kind of blowing this whole thing too much. And of course, people have even tried CCSDTQ. I mean, this is too much. Already people start criticizing that why are you doing this? I mean, CCSDTQ is totally, you have T3 and T4. Those T4s are not T2 square. Those T4s are genuine T4, four body coming together, right? So whenever I'm writing a Tn like this, they are actually n particle coming together and getting excited. So that chance when n is larger than 2 is very small. And that was Sinanoglu's major work to show that the pairs are important and not more than pairs. But 2 pairs, 3 pairs can independently come with a lower and lower probability, but they are effectively good. And if you miss that, and that is what CI does, if you miss that, you miss very, very important effects. And I will show you by an example how that effect comes in. Yes, yes. Exponential brings in these square terms because you have not only square, cube, everything. So how will you bring infinite order without an exponential series? Okay. So and then these factors also come very naturally. So exponential, because you have these factors that they are overcounted. So these factors also come naturally. The exponential series was also derived from the perturbation, exactly the way you said. Select the terms, go up to infinite order, resum it. And that was what Bruckner and Goldstone started doing. And they also got the same exponential series. So yeah, I mean, there is a much more mathematics to it. But once we know what it is doing, I think exponential series does in a way that nothing else can do properly. And yeah.
Question is, since you talk about CI and all that, how does it compare with MCHF?
MCHF is it's a multi-configuration, okay? But you are changing all the orbitals. The difference between CI and MCSCF is that in MCSCF, in CI orbitals are fixed, Hartree-Fock orbitals. The only parts that are just which are actually varied are the CI coefficients, linear coefficients. So you make it 1 plus T1 and T2, so these coefficients. I can call it C1, C2, just to make sure that it is CI. So only this, but no orbitals are not changed. In MCSCF, what will happen? I have determinants, I don't have fixed orbitals. So I will change not only coefficients, but orbitals, and hence MCSCF is much more expensive. So you have one CI equation, one SCF equation, stuck together. Yeah.
Take care of some of these perturbations automatically.
Right. So MCSCF is much more accurate. That is why MCSCF is much more accurate, computationally more demanding, and you have a CI equation, linear eigenvalue equation, and a SCF equation, and they are iterative. So SCF equation depends on coefficients, CI equation depends on orbitals, and it is a very, very complex process. One of our friends, GP Das, I don't know if you must be knowing his name, Chris Wall and GP Das, SC Wall. In fact, GP Das was, for a brief time, was an NCL for 2 to 3 years. He came back from US, you may be remembering. So he was one of the pioneers of MCSCF, of course, along with McQueenie and many other people who did it. So MCSCF is a bit different. It's certainly a nonlinear variation, but the orbitals have changed. In couple cluster, we are not changing the orbitals. Again, orbitals are fixed with the Hartree-Fock. With those orbitals only, we are doing everything else. All correlation we are doing with those orbitals. Okay, so I wanted to say how this linear and exponential varies physically. So let me take a simple problem of two H2 molecules, two hydrogen molecules, non-interacting. So let's say this is H2A, this is H2B, far apart. 100 angstrom, 200 angstrom, whatever, far apart. You can do the calculation. And this is the sigma G. I'm taking a very simple problem, sigma G square. This is also the sigma G square for the B, this is for the A. And now I'm doing a simple CI with a sigma U A square, sigma U B square. So I hope you see the model. I have done a 2 basis Hartree-Fock. So I've got a sigma G and a sigma U. And then what I'm doing is constructing H2 dimer wave function as a CI. So what will happen to the Hartree-Fock? Hartree-Fock will be sigma G A square into sigma G B square, right? Determinant of that. This into this. So that will be my Hartree-Fock for 4 electron. Then I have a double excitation. So what will be my double excitation? Either this, so they are far apart, so one cannot get excited here. That amplitude is 0 because they are far apart. But they can get excited here or here. So I will have a sigma G A square and excite this sigma U B square. Determinant, so with some coefficient. Let's assume these coefficients are same by symmetry. And then you have sigma U A square into sigma G B square. That's all, right? I have double excitation, so either from here or from here. Correct? What should actually happen in the region of interaction? That there should be a product of the double CI for the hydrogen, 2 hydrogens, right? So if you take now hydrogen A and hydrogen B and take a product, so what is going to happen is the following, that the first product is going to give you the Hartree-Fock. So you are taking a product of this plus this into this plus this, right? I am doing double CI for each of the hydrogens. So the first one will give you this, the second one is coming this, Third one is also coming, but there is a fourth one in the product. Fourth one is sigma u a square, sigma u b square. Because I am taking product of the doubles. So doubles and A, doubles and B, when I take a product, I have a situation where this is excited here, this is excited here, product of this. What is this? This is quadruples, which this cannot take care. Because I am doing blindly a double CI without thinking. So this wave function is not a product of these two wave functions. So if I have a product of CI, which is sigma g a square plus sigma u a square into, again, let's say I have some coefficient, doesn't matter, sigma g b square plus sigma u b square. So that is your doubles into doubles. These and these are not identical. Now, if the wave function at the non-interacting region is not a product of the fragment wave function, what does it mean? The energy will not be sum. That is a very basic quantum mechanics. That if Hamiltonian is a non-interacting Hamiltonian, the eigenfunctions are product, eigenvalues are sum. They are called multiplicably separable and additively separable energy. So you can see the wave function itself has failed to be a product of the two existing wave function, and that is the signal failure of CI. Double CI, after doing H2, cannot break the H2 dimer to H2 plus H2. So the message is the DCI cannot separate. So you are doing potential energy surface with DCI, it's dangerous. Right? Whereas if you do couple cluster, now this is automatically done because you have an exponential. So you have an exponential T2A into exponential T2B, that's a product, which is nothing but the full thing, which is exponential T2A plus T2B. Exponential is product separable, that's the point, mathematically, whereas a linear term is not a product separable. So the point is 1 plus C1 plus C2 cannot be written as 1 plus C, is not a product separable, or 1 plus C2 into A into C2B, it cannot be written as a product of AB. But exponential can be written. So exponential automatically takes into account the quadruple. So again, this highlights the importance of quadruple. But what kind of quadruple? Which is product of doubles. Right away you can say this is product of doubles. And that is exactly what, as I said, couple cluster is doing. That the T2 square, it is taking the product of doubles. And couple cluster is a very good wave function. So these are physical effects. I'm not even going into mathematics of couple cluster, which is all there, but that's not important. Physically, the wave function is a right wave function. Whatever you pick up, T1, T2, T3, it's all products are there. And that is most important. Because for size consistency, this is very important. What is size consistency? At large distance, A and B energy should be A plus B. Wave function should be product of A and B. Wave function should be product, energy should be additive. That is the meaning of size consistency. That is when I say it is separated. To do that, couple cluster is ideally suited. Okay? Of course, in this case, I have assumed something important, that the Hartree-Fock itself separates. The Hartree-Fock itself separates into this, I have assumed this. There are situations where Hartree-Fock itself does not separate, and I will come to that little later. There, even couple cluster will get into trouble for size consistency. So there are two very important effects. One is called size extensivity. In fact, a lot of confusion is there in the literature. So let me write these two down. One is called size extensivity. So size extensive theories are theories which scale properly with the size, where the energy is proportional to n. Interacting system, this is not non-interacting. So even when the interactions are taking place, the energy is scaling as a proportional to n, which means that's the dominant part. It doesn't mean there is nothing else is there, but there may be n to the power half, n to the power 1 by 3, but the dominant part is just n to the power 1 into some constant. So the energy changes like that. For large system, this is correct. If you look at the energy per particle, correlation energy per particle, you will get some value. That is called size extensive, and the couple cluster ticks there. Quite clearly, because of the exponential nature, one can show this. What is size consistency? Size consistent theories are theories which separate. So this is basically a separation, which means in the non-interacting region, EAB, non-interacting goes to EA plus EB. This is quite different from this. So these two are quite different. In case, and this is actually later understood, many people thought this is more complicated, this is easy to understand, but people understood that this is actually more difficult to implement. Like for example, when you do couple cluster with Hartree fog, if Hartree fog does not separate, if reference does not separate, this is I call reference, does not separate, then even if you use couple cluster, the separation is not guaranteed. Okay? Then CC will not guarantee, will not be size extensive, size consistent. Though CC is size extensive. The problem here is not with this correlation part. The problem here is the reference part. So there are, for size consistency, two things have to happen. The reference, Hartree fog or whatever you start with must separate, and then your correlation part must separate. Must be, or correlation part must be size extensive. So if you do CI doubles, for example, first of all, it is not size extensive. And these people have shown that this is basically, the energy is basically proportional to square root of n.
And the number of electrons.
Number of electrons, yes. But it should be proportional to n. The problem here is that as soon as this is, huh? Yeah, I mean the electronic energy, whatever you call, you can call it.
No, but it means the limit of the
Very large n, yes. So in the limit of very large n, what will happen if you look at the E by n, limit n tends to infinity, it will become 0. So after doing all of the correlation energy, it has all vanished. There is no correlation energy per particle. So that is why square root n is not good. N, there is no problem. At least a constant term will be there, which will actually survive.
It should be proved analytically because large n limits cannot be done numerically. Right?
It is analytical proof, yeah. This is analytically shown that E is proportional to square root n for CI. Double CI. CISD, it will be slightly better, n to the 0.55, 0.57. Triples, it will be even better. Full CI, it will become again proportional to n. That's very interesting. With full CI is an exact function, but we never do that. So this is the problem of double CI. So even if the reference separates, because this is not size extensive, eventually it will not separate. So for separation, you need two things. Reference must separate, and this must separate. So that is the reason people do multi-reference CI. Multi-reference CI, what is the advantage? Because of multi-reference, reference separates, guaranteed, and then the CI also becomes usually much more accurate because you have CI, SD on each of the reference space. So multi-reference CI is approximately size consistent. So you will see in all potential energy surface people use multi-reference CI. That is also motivated by the fact that the single reference does not separate at large distance. Even this hydrogen molecule, if you take it to large distance, Hartree fog does not separate. I hope all of you know this, that it overshoots the energy, right? RHF. So Hartree fog also, so even if you do H2 potential energy surface, it's a problem with couple cluster. Couple cluster on Hartree fog cannot do. You still require sigma g square plus sigma u square. Reference space, then do couple cluster. So ideally for H2 PES, you need minimum exponential, whatever, if you want to do T1 plus T2, that is okay. Plus into acting on some C1 sigma g square plus C2 sigma u square. I'm just looking at the symmetric state, G state of hydrogen molecule. This is for the hydrogen molecule. So this is good. Why this is good? Because I have guaranteed the reference to separate at large distance. I have also put the multi-reference part. This is indeed the most glorified theory. And this is known as the multi-reference couple cluster. Many of you might have heard MRCC. I will not go much into that, but I just want to allure in this context of thing that why do you do MRCC? If CC was good, because we still have a problem of reference space. And I'm giving a simple example of a hydrogen molecule which does not separate. Hartree fog does not separate. Even Hartree fog does not separate. So many people don't realize it. It's a closed cell system, but does not separate because the spins is a problem at large distance. So when does Hartree-Fock separate? That is a big question. First question. If a closed cell system, and this is the general rule, if a closed cell system, I am looking at a fragmentation to close plus close, then RHF is good. So, beryllium 2, beryllium plus beryllium, helium 2, helium plus helium, good. But a 4 electron system, I am looking at a separation of 3 plus 1, it's not good because it is open plus open. If you look at hydrogen molecule, that's what is happening. H2 separating to 1 plus 1, right? Hydrogen atom plus hydrogen atom. So anytime closed going to open plus open, remember closed is an even number of electrons, but they can have an odd number of electrons, some can be even, right? So RHF is not good. Restricted Hartree-Fock is not good. So you may have to do UHF, you may have to do multi-reference Hartree-Fock. Okay, MCHF, whatever. So this is the first problem of reference that you must worry about. After you have cleaned up the reference, remember CI is also not good because it is not size extensive. So then that is the reason we advocate, first you clean up the reference, then you do a couple cluster. Now it's a very complex thing when couple cluster acts on multi-reference. I'm not going to talk about the theory of that, but I'm just trying to point out the significance of MRCC. We have all done work on MRCC. Half of my couple cluster works on a multi-reference couple cluster. And many people ask, why did you do such complicated theory? It is because even this potential energy surface cannot be done properly. Is it clear? If there are any questions, because this is a tough part to understand size extensive and size consistent. Size consistency is a much harder thing to apply because you first need a good correlation wave operator, which is what is called wave operator exponential, plus you need the right reference, both. One of them going wrong, you are out. Whereas size extensive is easier because you are not talking of fragmentation, you are not talking of separation. Okay, so people actually worked on this a lot, and then that is why a couple cluster has been very, very provocative. So I explained that with H2 dimer. So H2 dimer wave function, Hartree-Fock is not H2 into H2 at the RHF level, of course. So this is the first problem that we teach in the classroom. Yes.
H2 dimer is like a closed system, right? And each H2 is like a closed system, isn't it?
H2 dimer, I meant H2, sorry. Not dimer, I meant H2. Hydrogen to hydrogen, sorry. Yeah, H2 dimer will separate. The Hartree-Fock will separate. So whenever you have a closed cell system going to, thank you for pointing it out. Whenever a closed cell system going to open plus open, it has a problem. Hartree-Fock has a problem because you are doing a RHF, the original fragments are not RHF. But if you do H2 dimer, then there is no problem. B2 dimer, again Li2 dimer you will have a problem because it goes to Li plus Li. So you have to be careful. So potential surface is very easy to generate PES. Li2, just run couple clusters, doubles, and then you get wrong results. Okay? And Li2 at least you can check if you have a more complicated fragments, which are, the dimer is closed shell, but when you fragment their open shell, you will not even know. Where have you got? And with that PES, you will start to do dynamics, you will start to do everything else. Interpret the reaction, where the reaction has gone, okay, how they are fragmenting, all of that will become wrong. So that is why it's very important to be a theoretical chemist. So I want to tell that computational chemist alone will not help unless you know these nuances. So that's very important. Yes.
One more problem.
Yes.
When you do the singles, Bridgman's theorem says.
Yes, I'm going to come to that. So yes, that's a good question. So I think he has put this point. There are so many things to discuss actually. It can go on whole one week. I feel this is a course, no? It's eventually a course. Okay, so I think I just want to go back to CI problem and tell everybody that if you do only CIS, so you have a Hamiltonian which is 0, 0, Hartree-Fock, and then 0 singles, It depends on how many singles are there. And then a single. I am writing in terms of blocks. I hope all of you know how to write block matrix. So matrices are in blocks. So what Professor Harbola is pointing out is a very important theorem that so these are basically determinant of singly excited interacting with the Hartree-Fock through Hamiltonian, and this is 0. Thankfully, this is 0, and this is the content of the very famous Brillouin's theorem. In fact, Brillouin's theorem is a direct consequence of Hartree-Fock variation. First order variation is 0. So this is basically Hartree-Fock. Now, if you diagonalize this, what will happen? What is the lowest energy? Lowest energy after doing CIS is just E Hartree-Fock. That is this, because this is completely separated from this. It is block diagonal. I hope you understand. These two blocks are separated. The 0-0 block and singles. So CIS just gives you Hartree-Fock. So if you want to do ground state energy, CIS is not good. But there are other determinants, other eigenvalues which come from this part. So CIS is usually used for excited state. So if you want excited state energy, you do CIS. Of course, forget about all the problems of CI right now. The CI is not good, I have already told you. But if you do this, you will be at least getting the excited state energies, and that is why people have done CIS as an excitation energy. It's not good for ground state because of Brillouin's theorem. So what happens if I use couple cluster? So that is one question that I would like to answer. So instead of 1 plus C1, if I now use CCS, okay, this is a very interesting thing. If I use CCS, which means my wave function becomes exponential T1 into Hartree-Fock. Now, forget about all separation problem. Hartree-Fock is good, and just looking at the energy, what will you get? So what happens here? There is a very interesting theorem. Again, it's a provable theorem by Thouless. It's called Thouless theorem. Thouless said, if you make any exponential single excitations on a single determinant like this will generate you another single determinant, let's say phi 0 prime, with different orbitals. It's a very interesting theorem actually. I mean, I didn't really believe it. Because you have so much of T1, T1 square, T1 cube acting on phi 0, which is going into virtual orbitals. And finally, Thouless showed that this can all be summed up to one determinant with different orbitals. Those orbitals are linear combination of occupied plus virtual orbitals. It's a beautiful theorem. So you eventually get a single determinant. Now the question is this single determinant better than the Hartree-Fock? Cannot be. Because we have already said Hartree-Fock is the optimum energy. And indeed Thouless showed that if you now optimize T1 with this, optimize T1, so basically do a variational calculation with different values of T1, you will get back Hartree-Fock. So this is another way, you have to put that. This is another way of doing Hartree-Fock. Very, very interestingly, start with exponential T1 on an arbitrary determinant and variationally optimize T1 amplitudes. Allow that to act on that arbitrary determinant, you will get a single determinant, and that single determinant, lo and behold, is Hartree-Fock. That's what Thouless said, that you will always get a single determinant, and since the Hartree-Fock has the minimum energy, if I optimize T1 starting from any arbitrary determinant, I will only get back the Hartree-Fock. So you will never have heard for the ground state energy exponential T1 Hartree-Fock theory. You have a CIS. CIS is at least good for excited states. CCS is good for nothing. Having said good things about CCS, CCS is worse than CIS, doing nothing. So the first thing in CC that is done is CC doubles. They never do singles separately. They first do couple cluster doubles. Then in the presence of doubles, you can do singles. So the first level of theory is CCD. Next is CCSD, then CCSDT and so on. Whereas in CI, you can have a CIS. Hartree-Fock will not change, but at least the excited states will be new. But you never do CCS. And this was very interesting theorem by Thouless. Again, it first came, many of these came in nuclear physics, incidentally. So those who are interested, many of these actually came from nuclear physics. In their couple cluster was by Kuster and Kumel in nuclear physics. So nuclear physics, they actually proved these. And because of this Thouless theorem, it became very interesting that T1s are nothing but just changing the orbitals. But C1s are not that. That requires exponential, that's the difference. In the case of CIS is not just getting a single determinant. That is giving you on diagonalization Hartree-Fock energy for a completely different reason. Because that Hamiltonian matrix between Hartree-Fock and singles is 0. It's a block diagonalization. It's a different, the physics is different, that's what I'm trying to say. Here, it's just a resummation physics. That all T1, T1, so you need those T1, T1 square, T1 cube, all that together to be resummed.
And some unitary transformation.
Yeah, it's a transformation to another set of orbital. So it's a unitary transformation, no doubt. So I think it's a very interesting, this part is very interesting. The Brillouin's theorem versus Thouless theorem. And that little bit different. Brillouin's theorem is Hartree-Fock. Thouless theorem is also Hartree-Fock. As I told you, if I don't know anything, I start from there, get optimized T1, I'll get Hartree-Fock. And Brillouin's theorem is also probably a consequence of Hartree-Fock. Okay, or even Hartree-Fock can be posed as a Brillouin's theorem. People have done that also. You'll see in the Epstein's textbook, a lot of nice appendices are there. So yeah, this is all very interesting things about the couple cluster versus CI. If somebody asks you, can you enumerate difference between CC versus CI? There's so many things to tell. So I'm just trying to give you some points. It's of course not over till it is over. So that will not be over at any point of time. So I just now want to tell you that to solve the couple cluster equation, of course now it is not T1 alone. It has T1, T2 at least, or just T2. CCD is okay. So assume that this is my Schrodinger equation. Then I project to the exponential minus t. Now you will see the beauty of the exponential function. So I wrote h exponential t Hartree-Fock as e exponential t Hartree-Fock. So the beauty of an exponential function is here. When I pre-multiply this by exponential minus t, h exponential, this will take little time. Oh, it's coming up. That's good. Phi Hartree-Fock. This part gets cancelled out. So you get just e Hartree-Fock, e phi naught. So if you look at this wave function, this equation, I originally started from h psi equal to e psi. Now I got a new equation where I have a model Hamiltonian, and this is the idea of the model Hamiltonian, or sometimes they call effective Hamiltonian, this, whose eigenfunction is the same as the Hartree-Fock, but the eigenvalue is the exact. This is a very interesting idea actually. So it's an intermediate Hamiltonian whose eigenfunction is the Hartree-Fock eigenfunction, but its eigenvalue becomes exact. For the full Hamiltonian, of course, the eigenfunction is also exact eigenfunction, and the eigenvalue is also exact. But in this case, it's a modified Hamiltonian whose eigenfunction is the original Hartree-Fock, and the energy is, however, the exact. So there are three equations. One is this, 1, this is 2, and there is a third equation where everything is not good. So if I have H0, 0th order Hamiltonian, on phi Hartree-Fock, then I will get E0 phi Hartree-Fock, which is basically the sum of the orbital energies. So that is how the perturbation theory starts. That so I can write these three equations, Hartree-Fock, sum of the Hartree-Fock Hamiltonian. So I can have H0, H, and a modified effective. This is called the effective Hamiltonian theory, that it gives you a reference space as the eigenstate in general, reference space. This is single determinant, but the eigenvalue is at least exact. And this is very interesting, the way to look into it. But again, this could not have been done if it was not exponential. Because if I do a similarity transformation with the CI, it will not cancel. Right? 1 plus C and 1 plus C inverse, if I do, it will cancel brute force, but it will not have the effect of the Becker-Hausdorff expansion. So I will show you the Becker-Hausdorff expansion, which makes it much easier to do. Yes. Huh? Yeah. So yes, sorry. So I did not use H. If you have seen, I have used H normal ordered H, Hn. I want to define Hn is nothing but H minus E Hartree-Fock. Very simple definition. And in second quantized notation, it's easy to write. So if you use normal ordered H, then everything that comes is correlation energy directly. So these are expressions which are directly correlation energy, but it doesn't matter. You can always subtract Hartree-Fock later. Yes.
Second equation, phi 0 will be there or phi h will be there on the right side?
No, both are phi 0. Phi 0 and phi Hartree-Fock is same. Yeah, same. I'm sometimes using phi 0, sometimes using phi Hartree-Fock. They are same. Yeah. So these equations are written in terms of normal ordered H. So I get directly correlation energy. So it's a direct equation for correlation energy. And then if I project the same thing with these excited determinants, depending on number of T's, if I have doubles, then only doubly excited. If I have singles and doubles plus singles, they will become similarly 0, because now this phi e to the power minus t will get cancelled, and you will have only phi star, phi 0. So they are orthogonal. So they will become 0. I hope it's clear, because as soon as I do e to the minus t, look at this equation. This is what I have got now, equation 2. So as soon as I put phi star here, this is going to become 0. All the phi stars are orthogonal to phi Hartree-Fock, singly excited, because it is the same Hartree-Fock orbitals through which I am generating. And so these are the equations, and this is the energy, and we have to first solve the equation, then we get the energy. So that's how it goes, and this equation is a nonlinear equation, as you can clearly see, unlike in the case, so it is not a linear eigenvalue equation, it is actually an algebraic nonlinear equation. Iteratively you have to solve, and this is the problem of coupled cluster. Because if you don't start with the correct T as a starting value, it may not converge. So usually we start with the T as a perturbation guess. And if the perturbation is good, it does converge. But that is one problem that the coupled cluster has, that the convergence is not guaranteed. All right, so I think I will not go. The important thing about that particular exponential minus t, h exponential t, or hn, doesn't matter how we want to write it, is that it has a Becker-Hausdorff expansion. And this is the second quantized way of showing that this is size extensive. Because whenever you have a commutator, one can show that in diagrammatics only link diagrams survive, and link diagrams are all proportional to n. Their values are all proportional to n because of this commutator. Because ht minus th will remain, disconnected parts will cancel. Disconnected parts are h and t, which are not connected. So either you do h or t and h, their results are identical. So in the commutator they cancel. Only the connected part remains between h and t. And you cannot have t and h connected, because t is only whole particle excitations. So only ht connected remain. So each of these is ht connected. In the Becker-Hausdorff expansion, I can write ht is nothing but, in diagrammatics, it is ht connected. That means draw all diagrams where h and t are connected. So similarly, htt is all diagrams where h, t and then t connected, t square connected, and so on. So if you use this series, you can get the whole thing is nothing but h exponential t connected. So it's a connected diagram. It has a energy is proportional to n. So to understand this, you have to learn diagrammatics. So again, there's a second quantization followed by diagrammatics. So if you learn this, you will realize why a connected diagram, there's a proof why a connected diagrams are proportional to n, each connected diagram. So the sum will be proportional to n. So there's a little bit more of physics here, and that is why coupled cluster is sometimes is very hard to go through each one. Yeah.
So can we take t to any order here? Or
Yeah.
T1 plus T2 like that?
So each t is T1 plus T2 plus T3.
So wherever we want to stop, we can stop.
That T connection is anywhere there. Here the important thing, it's a linear HT. So if there is a T1, then HT is HT1 plus HT2 plus HT3. And of course there are connected diagrams, so there will be a lot of possibilities will vanish, because you cannot connect. So it's not going to be so complicated as it thinks. And eventually it is not even an infinite series, because H has only certain number of amplitude lines. It is a two-body particle, two-particle operator. So not too many T's can get connected. And the T's cannot get connected among themselves, because they are all whole particle excitation. Their connection is also not possible. They all have to be connected through H. So there is a serious limitations. So it is hardly infinite series. It looks infinite series, but in actual practice, when I do the equations from phi 0 to phi star, they will not be infinite series. So CCSD fully truncates. Okay, so it's not an infinite series. Infinite series would have been if something that I started during my PhD and then we changed gears and did in a very different way. That is, if I would have written energy like a CI energy and variational energy, what would have happened? It would have phi Hartree-Fock, exponential T dagger Hn or H e to the power T phi Hartree-Fock. Now imagine what I am doing here. I am doing psi star, psi, H, psi. What is psi star? Psi star would be phi Hartree-Fock conjugate exponential T conjugate, T dagger, right? Now if I do this, the first thing that is going to happen is that this psi is not 1. Because T's are not, exponential T is not a unitary operator. So exponential T dagger exponential T is not 1. So psi is not 1. So that means the energy that I wrote is not correct. I have to divide by the norm. Right? So I have to divide this by norm, which is phi Hartree-Fock, exponential T dagger exponential T phi Hartree-Fock. That is simple. And now I can do a variation theorem. Now it has exact variation theorem. If I do variation, there will be an upper bound. There will be an upper bound just like CI. Okay, beautiful actually. And that is why we got excited. I'm talking of now 45, 47, 48 years back. Sometime we were very excited to do this, but then we realized that each of these numerator and denominator is a non-truncating series, unlike this. Why? Because H is still 1 and 2 body operators. The problem is, diagrammatically, T dagger and T can start, this is called contraction. They can start contracting. Because T is a whole particle operator, excitation, T dagger is a de-excitation operator. They can nicely fit with each other. And this can continue. Whereas, that is not possible because always T on the right, there is no T dagger on the left. So it's immediately dawned on us that both of these are non-terminating series, which is very bad because we don't know what to do. But then there is a theorem that we proved. Again, it came in a rather, I wouldn't say obscure journal, but I think the journal that today many people don't see except physics people. That was in Pramana. That proof actually came in Pramana in 1982. We showed that this numerator is nothing but this denominator. So if I write the numerator is nothing but this denominator into a connected part of e to the T dagger H, e to the T, but completely connected part. Though it is infinite series, but connected. But here there is no sense of connection also. I don't know if it is connected or not because there is no commutator. I can't write this as commutator. Then this denominator can be cancelled with this D divided by the D. The entire energy would now become just this. At least it is better than this by this. It has only connected series, which is good. So energy is proportional to N. But it's an infinite series. Initially, I could not even show that it is proportional to N. Okay, but this is not bad. So we started this, and this is today called XCC method. Expectation value couple cluster. People have truncated these by orders of, e to the power T dagger. People have truncated these by orders of perturbation, by powers of T, various ways one has done. And I think this is a very good method today. Later on, we move to another method, what is called extended couple cluster. I will not talk. And also unitary couple cluster. So that the norm gets cancelled. Today, because of quantum computing, a lot of people are taking interest in unitary couple cluster. You might have seen that that is an in thing. We did in 1980s. Never thought if people will have a second look at that. We got all the citations that we had to get within first few years. But now today people are citing. And people in the US are writing to me that I and Kudzenli probably were the first people with Debashish Mukherjee, Kudzenli, and then my paper. First papers on unitary couple cluster. So many people are writing to me, you should not have given it up. Truly that I didn't know that because of the regime of quantum computing, unitary will become so important. So my students are again reading my papers of 40 years back, which is not easy, I think, for them. So I told them to read my papers at least first. then we can do unitary coupled cluster. So I think a lot of these things happened. But these are all single reference coupled cluster. After this came the multi-reference, because I told you separation was a problem for the Hartree-Fock. So multi-reference coupled cluster. Can you now do the multi-reference unitary coupled cluster? Multi-reference XCC, multi-reference ECC, these are hard questions. Much of it is still not done. In fact, a glorified method that we are trying to develop is a multi-reference ECC. And there are a lot of problems we have not been able to develop. So I'm just saying there's so many things to still develop. Multi-reference XCC, multi-reference ECC, multi-reference UCC in the age of quantum computing. That is, do the same thing, but the reference is no longer phi Hartree-Fock. It is sum of many, many determinants. So that is a very, very important thing. I just want to tell, Professor Harbola was telling I did not talk anything about my work. So I'm just telling you what all I did. I'm not telling actually what I did. But there are so many things to do, as you can see, because of so many variations. So I call this alternative coupled cluster. And I'm trying to write a review article on that now, on alternative coupled cluster. Putting all my earlier papers together. And many of the others. And in fact, Bartlett also started taking interest in XCC. Then Piotr Pekush, Werner Kudzelnik, of course, did a lot of work on UCC, I must say. And several people were working at that time. Martin Hedgorden started taking interest in ECC before he moved to DFT. And his student, Van Voorhis, then followed it up with the ECC. So there's a lot of history of many of those people taking a lot of interest. And even Martin told me other day that you should not have given up. You gave up too quickly. I told my students deserted me, so it was very difficult for me to write the codes and all that. Sorry, yeah, tell me.
So UCC, when you consider UCC, the series will be converging, the number of terms will be less.
It is very complicated, no. Because what is this sigma? What is that? That T cannot be used. You have to use the anti-Hermitian operator. So it is T minus T dagger. You are right. But as soon as I write T minus T dagger, on the left side it will become T dagger minus T. On this side it will become T minus T dagger, and then you will see that they start to contract.
Oh, okay.
So it's a little bit more complicated than that. So that will be still a non-terminating series, unfortunately, UCC. But very much like XCC, actually, we showed later. But it has the structure of UCC that the norm is automatically cancelled. We don't have to show the norm cancellation. But so yeah, there are so many things which happened. In fact, if I have to speak on all this, it will take a lot of time. I thought I'll speak a little bit about conceptual reactivity. But since Pratim has done my job simpler, I thought I'll get back. So at this point, if there are any questions I can take on this part of the ab initio, because I'll change gears, as you know. So I wanted to say, I can go on and on, of course, on coupled cluster, lots of challenge, what we did, excited states. I have not discussed about excited states, so many things to do that requires, again, going into that is called static correlation, many of you know, multi-reference problems. So many things to do actually, but this is just the kind of tip of the coupled cluster. At least you should know why coupled cluster is better than CI. We have not discussed perturbation. Also, you should know that coupled cluster is selected terms in perturbation summed up to infinite order. These are two things that you should know, and that may be sufficient for the time being. So if there are any questions, otherwise we'll move to conceptual reactivity.
Any questions from the students?
Maybe you can elaborate on static and dynamic correlation.
Yeah, so static and dynamic correlation, static correlation is where there are determinants, there is a combination of determinants, each of them is large. So then you cannot do that by exponentiality. One simple thing is that the hydrogen molecule, if I have a sigma g square and sigma u square, they become very large at the separation limit, right? They become almost separate. If you start to do normal coupled cluster on sigma g square, the T operator which takes you from sigma g square to sigma u square becomes very large. And since coupled cluster is an iterative method, there will be a failure of convergence. It's a nonlinear equation. If amplitude becomes very large, what happens? It will not converge in general. So then what you should do ideally is that the large configurations, which is large amplitude, you bring them back to reference. and then do an exponential t which does not include scattering from those determinants, within those determinants. So that was the idea of the exponential t on multi-reference. So that is called static correlation, that reference space. So your MCSCF and all that could be like a static correlation, and then the exponential t is a dynamic correlation. Pure exponential t is a dynamic correlation. So that is why there is a combination is required, and that is why multi-reference coupled cluster is very hard. In fact, many people still don't like them because you have to be very, very careful in developing the theory. So in general, if there is a quasi-degeneracy or degeneracy or what is called, I hope you know the difference between degeneracy and quasi-degeneracy. Degeneracy is strictly the same. Quasi-degenerate means they are nearly same. In many parts of the chemistry, you don't have exact degeneracy because symmetry is not there, but they are nearly same. And those cases also have the same problems, so you have to handle them with the multi-reference. So that is the idea. Okay? Yeah. ECC I will not discuss, that is extended coupled cluster. If you are interested, we will talk later. Yeah, so extended coupled cluster can be done variationally, I agree. We have done that. Yeah, they are same. Number of terms are more. In extended coupled cluster, number of terms, the power series terms are more than the standard coupled cluster. XCC of course is infinite power, but then that is really not doable. So we gave up. Extended coupled cluster is where we stuck, but it has two sets of amplitude. One excitation amplitude, one de-excitation amplitude. That's how we are extending the power. So the left side is not exponential T dagger. The left side here is something else, which is a de-excitation amplitude, but at different values. So let's say some exponential sigma. That sigma is not T dagger. And then there is a double linking so that this will be a terminating series, and then you can do variation. So there is a lot of physics here. I didn't want to do extended coupled. Arponen first developed in Annals of Physics in 1983. That's the same Annalander physics that I talked about, Heisenberg's paper. Now they call it Annals of Physiks. And Jouko Arponen from Finland, he was the first to develop. Then Bishop came in, Arponen and Ray Bishop from UK. Heisenberg was Z-script for physics, not Annalander physics. Okay. Schrodinger, yeah. So okay, anyway, that's those are all history, but this is now Annals of Physics, that's for sure, Arponen's work. So I think it is good thing to, yeah. Any other question? So yeah, ECC is doable. A lot of people are today doing ECC, including Troy Van Voorhis, our group, Piotr Pikush has done a little bit. So yeah, a lot of people are now doing ECC. Yeah. Any other question? Okay. So then I will move to conceptual reactivity for the last few part. It became easy because Pratim has already kind of developed it. So I just wanted to tell some of the things that we have done, the new things. So first of all, Pratim has developed chemical potential, hardness, which we today call descriptors, which are global. Global meaning they refer to the entire system. Chemical potential is the entire system. There is only one value. Then he introduced local chemical potential, local descriptors, which have value at a specific point. Then he introduced condensed local descriptors, which have specific values for each atom. Right? So you move to the local descriptors. From mu and eta, I'm moving away now to the local descriptors. And the first one was the density itself, as he said. And then we discussed the Fukui function. So which is del rho r, del n. And as he said, there are many ways to calculate this. +1, -1, and average of that. So one of them is electrophilic, one of them is nucleophilic, one of them is radical attack, okay, which is neutral basically. But f of r is good but not good for chemists, because what do I do at a point r? Chemists are interested which atom is electrophilic, which atom is nucleophilic. Chemists are not interested at r. The density map is okay, Fukui function map you can give. Of course, the sum of the integral of the Fukui function will be 1 because it is n plus 1 or n minus 1. But I want to know something more in chemistry. Which atom is the reactive atom? So what do you do then? You take care of what is called the population of Fa on a atom A. So there is no function of R. So you have many atoms. So I think this is a very complicated thing to understand. Originally density is spread over all R. Now what you are doing, you are collecting their contribution to each atom. Every point has a contribution to each atom. It is not that atom A has only this is my region, this is my region, this is my region. No. The entire region belongs to every atom. But some regions they contribute more, some regions they contribute less, because the atom is here, so a surrounding region will contribute more, far away it will contribute less. So this is called the weightage. This is called a weight factor, and this is very important to understand that there is a weight factor of how the density is distributed to the condensed Fukui function. When I condense it, Mulliken, Loveday, they all do it, but I'm just telling you Hirschfeld, what is the behind it? So there is something called weight factor of this collection of the densities for an atom A. So if I know WA of R, this function, this is basically a weight factor function for a specific atom A. So there will be atom B, atom C, etc. Okay, so this is very, very important. So if I now condense them, so I have this Fukui function which is there for all atoms, and I condense them into A if I know the weight factor, and then do the integration with that Fukui function there, then what I am going to get is a population of electron on A. Because now I have collected all those density on the atom A, and I can get the population of atom A. So the weight factor becomes very, very important, and the weight factors are different from Mulliken, different from Loveday. In fact, we have 3 papers back to back in Journal of Chemical Physics where we have shown what are the weight factors for these. 99, 2000, 2001, 3 papers. So those who are interested can read. So the point that I am now trying to say that because of the weight factor, we got an idea of how to cheat and get a good Fukui function. That is basically the Hirschfeld population. The Hirschfeld population was independently known. What is Hirschfeld population? It is based on what is called Stockholder's partitioning. I don't know why there is a phone. Hello?
Good afternoon. Dear Indigo passenger, this is an important message regarding your flight.
Flight. Yeah. 4 o'clock. 4.
6011 from Chennai to Guwahati on the 26th.
They take too much time. Okay. So it is delayed. Thankfully, it is delayed by about 40 minutes. Not too much. No, that's okay. I mean, no, it should not be preponed. So that's why I was interested. So it is a little bit delayed, so no problem. Okay, good. So these weight factors are very important. Hirschfeld, what happens is the following. When you generate the cation and the anion, normally the weight factor should change because there is a relaxation when you are doing cation. One electron is less, one electron is more. So of course the entire thing should change, right? The density redistribution, density will redistribute. But in the Hirschfeld, what they did is that when I am doing +1 and -1, I will retain my original weight factors. So that was a very interesting idea that I have my like stock market, you have this as your weight factor. When you go to +1 and -1, the same weight factor is given to the n+1, n+1, n-1. Now, how does that help in Fukui function? And I am going to argue that this is good for Fukui function, not good in general. If you do Hirschfeld charges for cation and anion, they are not correct because at least they should be redistributed because you have now a new Hartree-Fock for cation, new Hartree-Fock for anion, everything is new, right? But stockholder partitioning artificially fixes this. So how is that helpful? If you look at the Fukui function, it is actually a derivative of rho of r with respect to n. What we are using here, n plus 1 minus n or n minus 1 minus n, is a gross approximation. So what should actually happen is the following, that you should use rho of r n plus delta n minus rho of r n divided by delta n in the limit delta n tends to 0, right? That is the actual derivative. I am not able to make delta n 0. So what did I do? I made delta n plus 1 and minus 1. So I remember I had a long chat with Bob Parr, and Bob Parr said maybe we may be able to do n plus delta n, but how I don't know, because I have to define the Hamiltonian. How do you define Hamiltonian of n plus 0.001 electron system, quasi-electron or whatever? But I think this is an interesting idea one can think of. But we don't have, so we did n plus 1 and n minus 1, which is a, yeah. They do it by ensemble average and all that, yes. That I know, that they do it. So this is the idea, is that I need actually delta n close to 0. Now what does delta n close to 0 mean in terms of weight factor? Tell me that the weight factor will not change. If change is only n to 0.0001, this redistribution will be much less for the cation and the anion compared to n plus 1 or n minus 1, right? Because I am changing very small. So now what I am doing, I am cheating. I am using n plus 1 and n minus 1, but I am artificially fixing the weight factor as the same. Hirschfeld population. So two wrongs make it right. First wrong is my delta n is wrong, plus 1 and minus 1. Second wrong is that I am using Hirschfeld population. For plus 1 and minus 1, they are not correct actually. But they eventually will give correct result because I am simulating the effect of delta n. Here actually it should not change. Now obviously this is a qualitative approximation. I can't quantitatively prove they are exact. They will not be exact. But what happens is that because of these, the results are much closer to what it should be. What it should be, that's the first question. The argument is the following. Because delta n is very close to 0, if you add a small number of electrons to the entire system, in the n plus 1 electron system, the density at each atom should only increase and not decrease. Now this is a intuitive, I cannot prove it. In fact, Parr and Young wrote a paper in which said that this is intuitively positive. Fukui function should be intuitively positive, condensed as well as f of r, because I am adding a small number of electrons. So it should not disturb any of the dense weight factor. So that delta n should be redistributed at every point, at every atom, and of course then you divide by that small quantity, you will get a reasonable number. So they argue that the Fukui function f of r should always be positive, intuitively positive at least. There are a lot of counterexamples, particularly for condensed. So we use the same argument that we condense it, but the way to condense it is to use the Hirschfeld population. Hirschfeld population is just a way to condense it. How do you distribute them over different atoms? So n and n plus 1 artificially have the same charge distribution, same weightage, and then I calculate the number of electrons by integrating with the density. So density is everywhere there. So I integrate over density over d cube of r, I will get the total number of electrons. So basically what I am doing is the following, that I am doing n of a as an integral Wa of r times rho of r d cube of r. So the entire density I am integrating with a weight factor for the atom A, and that gives me the total number of electrons in atom A. That's the easy formula. So now you see the weight factor is same for plus 1 and minus 1, only the density will change, and that will result in the Na for the cation, Na for the anion, and then I take the subtraction. And that subtraction is more likely to be intuitively correct. So the Hirschfeld population more correctly will give you the results. As he said, there are of course exceptions, because this is not provable. That the error cancellation is only a hopeful scenario, which happens in many cases. In fact, our papers are cited mostly by biologists. I was surprised initially. A lot of biology people are applying this and they get good results. Because if you have minus as a Fukui function, how do you interpret this? Because Pratim was telling that if you have a condensed Fukui function large, then it is electrophilic plus nucleophilic if it is largest minus. But what is large if it is plus and minus? How do you compare? Do you call plus 0.1 larger than minus 0.1? Or do you take a modulus? So there is so much of confusion which will come. If it is all positive, there is no confusion. And that is what it should be. I again repeat, there is no proof that the f of r should be positive, definite. No proof. Anybody can prove it will be good. The only thing I can say is that is this intuitive proof that since the delta n is very, very small, they should redistribute in a positive manner, and then the difference should always be positive. Because I'm again repeating, because I'm using delta n as plus 1 or minus 1, I'm now simulating this effect by using Hirschfeld population, which artificially does not change the weight factors. So WA for n plus 1, n and n minus 1 are identical, and then I get the number of electrons, and then they are, hopefully they get better result than Lovedean. I have seen Fukui function in Mulliken and Lovedean, randomly they become negative. So many are negative. Hirschfeld at least is much better. No, I mean,
All others can give negative, but now there are counterexamples in Hirschfeld also.
that's what I'm trying to say.
Hirschfeld is also
That proof is not proof, no, it is just intuitive. So many systems it may fail, but there are more likely to succeed. This way.
physically you must know what Fukui is telling. That suppose if you are throwing an electron to a molecule,
Yeah,
you will assume some electron density or population will
to
go to
increase, yeah.
Now I am adding an electron, but you will see that some
Depletion.
electron is coming out
Ah.
from
That is because of relaxation. You see, what is happening when you have n plus 1, n minus 1, the things relax.
but some atom in a molecule is losing electron.
Because they have sunk.
Physically, it is difficult to conceive.
So delta n, this will not happen. So that is why they say Fukui functions are intuitively positive. And we have simulated that effect with the Hirschfeld population. So that is one thing that I wanted to tell, which is something that we have done. The second thing is that he was talking of many descriptors. We have also done with Paul Geerlings and others, a descriptors which are called relative electrophilicity and nucleophilicity. So he said, yeah, that's okay. Dual descriptors, F plus, F minus, F plus minus F minus. That's a dual descriptor. What we have done is F plus divided by F minus. So this is called the relative electrophilicity. So this is something new. So I'm just highlighting what we have done, which is not covered. And the relative nucleophilicity is just the reverse of it, which is F minus divided by F plus. Now this work well, not for intermolecular, but again for intramolecular reactivity. So these are good for intramolecular reactivity. So within the molecule, which is the most reactive atom, which is most electrophilic, most nucleophilic, you can do by F plus, you can do by F minus, you can do by dual descriptors, whether it is positive or negative, or even by this. So it also something that is new and it worked well. See, please understand, entire descriptor theory is a qualitative theory. So this is not like couple cluster. Okay, so that is why I'm saying there's a change. In the couple cluster, I can tell everything correct, but here there would be exceptions. For everything that I tell, you can find an exception, which is okay, but you need to do still simple chemistry. Yes?
Sir, when they are say isolated atoms, you have their orbitals.
Yeah.
And when you bring them together, you form a molecule. Their
Right.
orbitals they add and subtract, and there's a linear recombination, and you form molecular orbitals. So when you say that at any point the electron density contributes to each atom,
Yes.
so is this contribution based on this redistribution? And
Yes, of course, of course. From the atom, if you look from relative to atom, yeah, it is because of redistribution, of course.
In that case, these weights that distribute the density to each atom, shouldn't they be specific for each molecular orbital? Since
No, the
each
density, no, the density, the weight factor is overall R. Overall R. So you can say that each atom had an original weight factor. So original Hirschfeld population is just this, that you carry the atomic weight factor to the molecule.
So I'm saying that at a point, there are two molecular orbitals. So it is possible that they will have different contributions to each atom.
No. This weight factor that we are discussing is the overall weight factor. WAR, overall weight factor of the density to atom A, taking into account all the molecular orbitals. But what Hirschfeld originally did is that he took the atomic contribution, like the two atoms A and B come and contribute to form AB. So they had their own share of electron density, right? What Hirschfeld said is that let us freeze the share. So you come with your stock. Now when we deplete or we increase our density, the increase or decrease will be according to what stock you had given me. If you are 100 rupees, 200 rupees, you'll get two times more. Because you had only 100, at 200. So basically that atomic thing that you are saying is very important. That is how the concept came. That the atomic, but I didn't go into the detail how the weight factors are decided, but they are decided based on their atomic contributions. Each atom has a density, right? Each atom has a weight factor, which is different, but when they come together, the same contributions are carried over. Whether it is AB plus, whether it is AB minus, as long as the atoms are there. Yeah.
This fixing, is this like saying that the first order change, the redistribution will not be there, so we could fix? For example, in Bookman's theorem, you take an electron.
Yeah, so of course, at higher order this will all become wrong. Yeah, I mean, see, this is anyway qualitative theory, I hope you understand. And the idea is that if you go to higher order, delta n square, delta n cube, they are all becoming smaller and smaller, right? So in that sense it will work. But as I said, there are exceptions which have the failure of this. All right, so this is another descriptor which is called relative descriptor, which you did. And the third thing, the final thing that I want to say is that we also developed, like an HSAB principle, a local HSAB principle. So I'll just give you the basic idea of the local HSAB principle. So if I have a and a B interaction, so I have an interaction between A and B, and I know that this is a molecule, this is another molecule, and here is an atom K, here is an atom L, which are actually interacting. So the bond is formed between atom K of A and atom L of B. How do I know this? This I know by these qualitative descriptors, which is electrophilic, which is nucleophilic, right? I mean, not F plus, F minus, but Fk plus, Fk minus, and so on. So condensed Fukui function, I have them. So I can tell you this is more electrophilic, this is more nucleophilic, so they will attack. So that is the first thing that one can do. So catalysis and all that, these are very useful problems to know where the attack will take place, the first attack. So you design your problem. Now I am saying if there is the only point of attack, there may be multiple attacks, can I calculate the energy of interaction, A and B, when the attack is taking place through a local site of A and a local site of B, which I have identified, without doing a calculation for entire AB. So I need only a calculation for A as much as possible, calculation of B, and maybe we have a parameter which is an overall charge transfer, which is easier to see somehow from the chemistry, that if there is a charge transfer of +1 overall electron, I should know this charge distribution. Can I find out the energy without doing the full-fledged calculation of AB? Because this is the largest time. EA and EB is easy. This is the largest calculation if I do the entire dimer, entire fragment, entire system, species. So if I know the fragments A and B and their Fukui functions, which are easy to calculate, chemical potentials, hardness, can I actually calculate the energy? So this is what we attempted in the local HSAB principle. Again, these are not accurate. These are all qualitative things. And then second level we attempted was like DNA base pair, where there are multiple sites of interactions. So can I extend this from one site to multiple sites by summing over? And we did a lot of things by simply summing as if they are non-interacting. If they are interacting, they have a cooperative effect, then how to sum up. So, lot of developments we did in the what we call local HSV principle. Let me see, let me just try to show one formula for that, if I can. I had that second thing, no? Anyway, I can start this, yeah. Yeah, just before I move ahead, I must tell you one more important work from where I actually started. Can you do it full? Since I am on the slide. Yeah, so where I actually started is this slide that we showed, that Pratim has already shown, is how do you prove the principle of maximum hardness. So remember, hardness was I minus A by 2, and you can take a delta SCF. As he said, I can be calculated by SCF, A can be calculated by SCF, and then subtract. You can have a Koopman's approximation to delta SCF, which is simply homo-LUMO, right? LUMO minus homo. So all that can be done. What we did was very interesting. We actually did an IAA calculation by couple cluster, which means not just delta SCF, we did correlation, full correlation. So we calculated ionization potential and affinity by a couple cluster calculation. That was my early days, 93, because I was still doing only couple cluster. The problem came to me, I said, why not calculate ionization and affinity by couple cluster, because we are doing that all the time. So the code was just there. So we took a very simple, I want to tell something, we took a very simple molecule, water. Okay. So there are symmetric and asymmetric states, the bend and all that. What is interesting is that we saw that if you have an asymmetric stretch, you can keep the chemical potential constant by properly stretching and bending. So many of the asymmetric stretch points are equichemical potential. If you take this out, start from a symmetric stretch and then make asymmetric stretch such that all of these have the same value of chemical potential as the symmetric stretch. And then we clearly showed that the hardness is maximum here. The symmetric point is the point of maximum hardness. The harder configuration is more stable. So what we did is that we searched through the constant chemical potential. So there is a very important part in the principle of maximum hardness, that the system goes to a largest hardness system which has equal chemical potential. Among those configurations, the one that has maximum hardness is the stablest configuration. Many times we forget that constant chemical potential. That is part of the principle of maximum hardness statement. And I thought, let us do this. So we generated equichemical potential points by simply trial and error. You can keep changing. Then all asymmetric stretch will, because this will, if you keep on do a symmetric stretch, it will never be equichemical potential. Chemical potential will keep on increasing or decreasing, right? That's a monotonic. So the only way to keep it is stretch one bond and decrease the another bond. And then among all those potentials, we found that indeed this symmetric one is the most stable. That is the first point. It does not still prove the maximum hardness principle. Then we showed that among all the symmetric points, the one which has the water is symmetric, as you know, one which has the experimental geometry is the lowest of the maximum of the maximum. So there are local maximum. You understand? Each symmetric point is a local maximum. Then the actual experimental geometry is the maximum of the global maximum, you can say. Just like in normal optimization, you do local minimum, global minimum. So that has a very clear proof of the principle of maximum hardness. A very simple molecule like water. So I just want to show you this. This is a very simple exercise we did. And this I and A, of course, this hardness was still calculated wrongly because we used +1 -1. I already told that is not correct. But at least we did a couple cluster calculation for ionization and electron affinity. So for every point, let's say I have some R1 at some angle. So this is a locally maximum. The hardness is maximum here. Okay, for all for this chemical potential. Let's say the chemical potential is mu A1. Then I go to another configuration, R2, R2. Again, it's a symmetric point is the locally maximum, but the chemical potential is, let's say, mu2, because the chemical potential will be different. So under each chemical potential, this is a local maximum. That is something that we can tell. Then we started comparing between the local maximum. That became a very difficult task because chemical potential will no longer be constant. They keep on changing. But at least we found that the experimental geometry, the hardness was the maximum among all the local maximum. So that was a very interesting idea that we got. It still does not conclusively prove the principle of maximum hardness. People have proved in many other ways. Like they have taken randomly some molecule, this molecule, calculated hardness, and so this is larger, this is stable. But here we are trying to do a much more accurate calculation, proper calculation, and all of these I and A are now couple cluster calculation. So that was the very first paper that attracted me in JPC. We did 93. Before that, I was not working on reactivity. Pratim knows this. So this is what attracted me, and this is because of a student. I must tell his name now. He is in BITS Pilani. So the student, I gave him to work on double perturbation theory. It was very, very interesting thing that Dalgarno and many people came. One Sunday morning, he came to my house and he told me, Sourav, it is not possible for me. I don't understand so much of mathematics, algebra. So then he started reading and he came up with I said, I want to do on qualitative theory, reactivity theory. Then he came up. Then I said, good, we will mix and match. You don't have to learn couple cluster, but the code is there. You at least do a better calculation so that we go little higher than the normal. And that is how this work came. Ramkinkar Roy is now, of course, quite an established theoretical chemist in BITS Pilani. He was also the head of the department and so on. So I think it was a very interesting way that we came because he simply declared that he cannot do what I gave him. So then he chose his own problem. So the students are very important. They determine the destiny of sometimes the PIs. Otherwise, I would never have gone into this probably because I was so much sunk in couple cluster. I thought everything else is not right. But here also we did couple cluster, incidentally. So I was happy. So to mix and match. Okay. So yeah, all this Pratim has already told, local softness, condensed descriptor. Yeah, so this is the local HSV principle. I just wanted to end with this energy formula that you can see that I have chemical potential of A, chemical potential of B, total global softness of A and B, and then I can actually, this is local softness, sorry, SA and SB, and that I think there is some error. One of them is local softness, one of them is global softness, both of them are not capital S. So the point, this is the point of interaction which Parr and co-workers had actually written, but not with the local descriptor, sorry, this is not with the local descriptor. And then Mendes, Pratim knows him well, Gasquez and Mendes started working on this, and now we can see there is a local Fukui function, there's a global softness and local Fukui function, they're stuck together. But the formula is interestingly, apart from lambda, it only depends on A and B separately. And this was a paper that which came, and then we investigated the lambda, the value of the constant, as the charge density, and then we published a paper for DNA base pair and several systems. We actually extended this for models where there is a multiple interaction, not one interaction, like in DNA base pairs. So we had localized reactive model where it's just sum over these and so on. So I think there are a lot of interesting things one can do, and so this is because today when I calculate, if I know the reactivity, then catalysis, I can quickly have an interaction energy. These are very quick, dirty calculations, which are okay as a qualitative theories, because all these theories are qualitative. The entire area of conceptual reactivity is the qualitative theory. All right, so I just wanted to point out something that we have done which he did not cover. And there is a lot to do, of course, because these are qualitative theories. A lot of you can take interest and come and work on this field. Okay, those who are not interested in very highly quantitative theories like couple cluster and so on can do. And the code writings are also fairly easy because you only have to get the population, then condensed Fukui function, all you need is charges. Okay, we have written this in terms of density on atom, but if you do charges, it will just become different, because charges are just negative of that. It has the nuclear charge minus the electron density. So you can take the charges which are there in every code. Hertzfeld population analysis you do, you get the charges, calculate Fukui function, and then start doing. So writing codes and all that, there is nothing. And then this delta E interaction also you can do. Just a simple formula coding. So it's really very easy to do. You don't need to be a great coder, but on the couple cluster and all that new thing, you have to really understand the codes, develop, you have to know how to handle 2 electron integrals, a lot of things are there. Here you don't have to do, because the program is giving you. And remember, I'm calling it density, conceptual density functional theory, but all of these parameters can be calculated without density functional. Like I and A, I calculated through couple cluster. So there is no reason to use DFT to calculate anything. Why am I calling it DFT? Why is it in DFT workshop? Because it's called conceptual DFT, because the concepts are derived from density. But once you derive, the density and its variants can be calculated by ab initio theories. Charges are there in ab initio theories also. But these concepts are originally, chemical potential concept was originally discussed by from the density. Then del rho, del n, Fukui function is also coming from density. So that is why it is now in the DFT parlor. But conceptual DFT is really different from computational DFT, where you're more interested in developing exchange correlation functionals and so on. This is somewhat different area compared to that. So I think, so that is why many people may like this, but there are a lot of physics and chemistry that you can do with this, which is a good thing. DFT is more of algebra. Here there are a lot of interesting things you can do. So those who are interested can get into this area. That's what I'm trying to tell. And you can use any program. You need not use DFT program to do this. That is the most important thing. Charges are calculated by any program. Finally, those are calculable by any program. Yes.
Okay. Thank you very much for the wonderful lecture, and really we enjoyed the entire journey from the couple cluster and using the couple cluster derived quantities in order to calculate the chemical descriptors.
So I jumped from couple cluster to DFT with that bridge.
Bridge, yes.
After jumping there, I ditched couple cluster. I went in that boat,
Yes.
But to get into the boat, I needed a couple cluster bridge.
If you have any questions,
Mental.
students, please feel free to, we have little time. So if you have any questions, we can.
Yes, any questions?
So to begin with, maybe I will ask one small question. So as you mentioned already, these chemical descriptors are only qualitative, but are there any descriptors that can be entirely computed, for example, using couple cluster or something like very accurately? Can we see any such, we understand that ionization potential.
So that descriptor has to be a quantitative descriptor, first of all.
Correct. So
Calculation
what are those
is
kind of descriptors?
So density itself.
Density is, of course.
Electron density itself, for example, is an exact thing that can be calculated. Electron density, and there is nothing qualitative about the definition of density.
Correct.
Right? Density is a exact definition of the electron density. But from the density derived, whatever you are doing, they are exact, they are qualitative. Like, because we are not able to calculate del rho, del n, many of these are qualitative because there are derivatives, and we don't know how to calculate derivatives with the number of particles.
Correct.
With external field, we can calculate. So I did a lot of work, which I did not show, on electric field effect on the Fukui functions. One of my students, Rahul Kaur, did PhD on that. He is now in Dibrugarh University. So what happens if I do electric field on a molecule? How does this electrophilicity, nucleophilicity change? Which direction they do increase? So a lot of interesting things you can do. But the problem is that the Fukui function itself is not calculated exactly because of del del n. So del del n is the problem. Chemical potential also has del del n. Hardness has del square, del n square. But if you want one descriptor which is absolutely accurate, density.
Okay.
We can do couple cluster density.
Yes.
Yeah? And density is a good descriptor. Today also people believe in density.
Yes.
Right? Just look at the density map. People know where the electrons are. So it's a good descriptor.
Okay. Any other questions? Participants? Yeah.
Yeah. Yeah.
Reference, like a perturbative guess for the parameters. Why are we relating the perturbative parameters to the?
Yeah, so because I need some guess to start my equation, right?
Yeah.
So I know that the T is nothing but the first correlation parameters. So if I look at the first order perturbed wave function, I have something which I can relate to T amplitude. So that will be basically the V IJAB divided by the orbital energy differences. EI plus EJ minus EA minus EB, that comes in the first order perturbation.
Yes.
So if I call this T amplitude, T IJAB amplitude, it is not very far from the truth. And that is the reason perturbation amplitudes are quite good. But if the perturbation theory itself fails, then you are in trouble. So we are basically going by first order perturbed wave function and then assigning the amplitude from there. So first order perturbed wave function is what? Hartree-Fock plus sum of the doubly excited with some coefficients. Those coefficients are my T. Okay, but these T's are now much more refined. It has an infinite order corrections. But to start with, I can do that. And usually that works. Usually in most of the cases it works. So that is the main reason.
But if degenerate, close to degenerate,
Then it will be a problem.
blow up and
Yeah, then it will be a problem. Yeah. That's a multi-reference. Then you have to do multi-reference theories. So then the simple T's will not work. Yeah. Yeah, degenerate cases are always very difficult. I agree.
Thanks. Yeah. Any more questions? That's a very interesting question.
Yeah, this is a good question.
No more? Everyone is
Yes.
moving? Okay.
So like you said, for degenerate orbital like F orbitals, in few
Degenerate?
orbitals like F orbital, so couple cluster is better or CI?
What do you mean by degenerate orbitals?
Or degenerate whenever energy
No,
levels
no,
are
you want to get the orbital density, you want to get the total energy of the system,
properties of F F elements like Lagrange.
properties of the F element is different. Like if it is like F element atom, then you're looking at the property of the whole atom. It just doesn't have only F, the other orbital.
But energy levels will be like
Energy of the F orbital. Only. First of all, let me tell you that as soon as you go to beyond Hartree-Fock, the orbital picture breaks down. Strictly speaking, there is no orbital picture, because orbital picture is only in Hartree-Fock. So we have to define what is F orbital in couple cluster. You cannot define that orbital. You can define the total density of the system. You can define the energy of the system. We can do a AIM, atoms and molecules, in a molecule to find out what is the contribution of each atom. You can analyze the population of all atoms in a molecule, but population of orbitals is really not a correct description for a couple cluster, because when you go to the correlated theory, we are going away from orbital theory. So that is why you can't get back and answer this question exactly. If you say, I want to get the electron ionization from the highest orbital, let's say that's an F orbital, that I can answer, that's ionization potential, that I can answer. But that is not just F orbital, it's the contribution of all orbitals actually. So, but that you may be right, because dominantly from F orbital, that my chemistry tells me. Okay, but I am giving you a total contribution of the entire system. So that is why it is difficult to bring back the orbital picture when I go away from Hartree-Fock. Because now there is a mixing, there are so many orbitals. Like there are virtual orbitals, occupied orbitals, lots of things are being mixed now. So it is very difficult to say. But the Hartree-Fock you can say what is the thing, and their dominant character remains, I would say. Yes, in the Casa-Safe you define active orbital, so that will be same if I do multi-reference couple cluster. Because I have to define a multi-reference space, so that I will define active orbitals are good, but they are only to define my configurations. Having defined this configuration, when I am doing the calculation, I am going away from the orbital picture. Orbital picture was only a starting picture. But remember, at the end I have gone away from there. So that is the hard part to understand. The chemist I already told yesterday, the chemists like orbitals. Okay, and so you are coming back to the orbitals. Without orbital you are not happy. But unfortunately couple cluster doesn't have orbital strict sense of the term. But I can tell you ionization, first ionization, second ionization, everything I can tell you from the excited states of n-1 electron. Now you have your own take, the first ionization from the F, second is from this inner F, D. Okay, be happy. I can't. Density is there, total density. Total density is there. But if you want an analysis of that kind, AIM, people have done that. But all AIM analysis is arbitrary, just like Mulliken, Loveday. That's what we have been discussing. Hirschfeld. So he also said all population analysis is arbitrary. You know, there is a very nice thing in Szabo and Oslund, if you read this, that when you do Hartree-Fock itself, you have total number of electrons, which is trace of rho S, where rho is one electron density matrix and S is the overlap matrix. So trace of these two matrices. Rho is actually called charge density, that is called charge density bond order matrix, P. But then you know that trace is invariant under commutation, permutation. So PS can become SP. PS can become S to the power half, PS to the power half. And S to the power 0.3, PS to the power 0.7. All of them are N. And now, if I take only sum over atoms of A, that will become one population. Unfortunately, the partial sums, when you are doing over different atoms, they are not invariant under trace. The total is invariant. That leads to different population analysis. Read that Szabo-Oslund text. That is a very important thing. That is how the Loveday is done. Instead of PS, they take S to the power half, PS to the power half. You understand what I am saying, no?
Yeah.
That since it is invariant under permutation, I can write trace PS. This is equal to total number of electrons. And then they say that if I take PS over different atoms, sum over all basis functions of I on an atom A, then it becomes Na. This is over all basis functions. But if I only sum over A, then it becomes Na. But now, if I start, instead of trace PS, trace S to the half, PS to the half. That is also equal to N. And now I can say sum over I, basis functions over A, S to the half, PS to the half will be naturally my Na. Sum over all of these, sorry, this is this is will be Na. It's a trace. So I'm just summing over the diagonal terms. And the total sum will be trace. But this trace, this sum and this sum are not identical. What is identical is this too, when you sum over all basis functions. But if I do partial summation on A, they will not match. But A, B, C, all of them if you add, then it is correct. Something will be more, something will be less. The trace is invariant. So this S to the half, I can do S to the 1 by 4. I can do S to the 3 by 4, no problem. Because first I did S to the half, then I put S to the half here, because it's under commutation I can do. And now you can see, you can have your own population analysis. Not Mulliken-Loveday. You do another population analysis. By having different S on the left of P, different S on the right of P, and if you can show that is better than Hirschfeld, Mulliken, Loveday, you will be famous. It's so easy to be famous actually.
Okay, so probably with that we will stop.